All right, so we've talked about these thermodynamically favored and disfavored reactions, but there are still even other reactions that can be thermodynamically favored and not occur. The reason being is that we have kinetics, right? So it may be thermodynamically favored, right? We can be thermodynamically favored, but still not occur if we need certain kinetics to occur, right? So maybe thermodynamically favored, dynamically, there we go. If it is thermodynamically favored, right, our delta G naught would be less than 0, but there may be kinetic control. Okay, so oftentimes when we're thinking about reactions, we think about thermodynamic control versus kinetic control, things like that. Okay, so this happens all the time. We kind of have to think about thermodynamics and kinetics all the time. Okay, but our thermodynamically favored reactions, we're going to come back here and we're going to start to apply our thermodynamically favored reactions. So thermodynamically favored reactions, right, our delta G would be less than 0. If they're thermodynamically favored, that means that our products are favored. So what that means, right, if we think about products being favored and we think about equilibrium, that means our K value is going to be greater than 0. Okay? So if we are thermodynamically favored, delta G naught is going to be less than 0, right? We're going to have a negative delta G. But if we are thermodynamically favored, right, we are products favored, our K value, right, is going to be greater, not greater than 0, greater than 1. Okay? So this Gibbs free energy thermodynamic control talks about that equilibrium. Okay? And we can relate those two things using these equations. Okay? So this is the equation that's on our equation sheet. To get to this equation right up here, right, it's just rearranged. So we've taken this equation, rearranged it to get to that. But this equation is on our equation sheet, right? So if our delta G is negative, right, then our K is positive. We are favoring those products, okay? And this is a really big point. We should know this, okay? We really got to know this, that if we have a negative delta G, right, that is a thermodynamically favored reaction, which means that we're favoring those products, which means that our K value is going to be greater than 1, okay? So how do we get some of these thermodynamically unfavored reactions to occur? Well, the way that we can actually do it is that we couple it with other reactions and make the overall reaction favorable. Okay? So this happens all the time, right? It happens with batteries, right? If we are charging a battery, right, it doesn't want to charge up. We have to kind of force it to charge up by coupling it with another reaction. This also happens in photosynthesis. Okay, so photosynthesis is not a thermodynamically favored reaction, right? We're taking CO2 and H2O, we're putting them together, so our entropy is decreasing to make those sugars, and, right, we have to put energy into the system rather than letting the energy out. So the enthalpy is a positive number, right? So it is not thermodynamically favored, but we can couple it with other reactions to actually still produce that sugar, okay? So this happens all the time where we couple those reactions together, okay? So now what we're going to start to talk about is an application of these things, okay? So our application is all about electrochemistry, okay? So our electrochemistry, we're going to remember some things from last year, but we're going to first of all talk about two different types of electrochemical cells. We have galvanic cells and electrolytic cells, okay? So galvanic cells are thermodynamically favored. Okay, so they are reactions that are thermodynamically favored. We don't have to do anything to make the reaction occur. An electrolytic cell is thermodynamically disfavored. Okay, so if we remember from earlier in the year or maybe from last year, right, we've talked about oxidation reduction reactions. We can remember the term oil rig, or we can remember the term Leo goes Gur. Okay, and that's telling us with our half reactions whether or not we have an oxidation reaction or a reduction. So if we are losing electrons, that's an oxidation. If we are gaining electrons, it's a reduction. Or oxidation is losing, reduction is gaining. Okay, so oil rig or Leo goes Gur, either way that helps us remember what's happening or identify what's happening with our oxidation or reduction reactions, okay? We also then can talk about our battery here, where we are going to have a cathode and an anode, okay? And we have another way to kind of remember which one is the cathode and the anode. We have a red cat and anox, okay? Anox, right? Ox, you have an O, so you know you have to have an, not a. So anox, that is going to happen at the anode. Red cat, right? Cathode reduction, okay? So we're going to start looking at this diagram right here, okay? So this diagram, right, would be a cell, right, an electrochemical cell, and we are going to have a thermodynamically favored reaction here, okay? So we need to talk about each of the different pieces of this electrolytic cell, okay? So over here, right, we have it labeled as the anode. So at the anode, we are going to have an oxidation reaction, okay? So the oxidation reaction, right, is going to be losing electrons. So that means that our copper, right, is going to be losing electrons. Those electrons are going to travel up this wire, okay? So you can see our electrons are traveling up that way. Our copper, right, it is starting as copper 0 and going to Cu2 plus and 2 electrons. Those 2 electrons travel up the wires. Our copper then, right, is going to become Cu2 plus and go into the solution. We are going to lose mass of this anode, okay? So we're going to have that solution there, and we're going to have Cu2 plus that's going into the solution. This is our anode, right? It is going to be the oxidation reaction. Over on the other side here, we have the cathode because we have a reduction reaction, right? We have Ag plus is going to be gaining 1 electron, right? And it is going to be overall going and forming Ag solid. So at our cathode, we are gaining mass, right? We're gaining mass solid on that cathode. The anode, we are losing mass of the solid. At the cathode, we have an electron that is going to be coming from the wire and attaching to an Ag ion. So we are going to be forming that solid on our cathode. We are gaining electrons, so that is a reduction, right? Red cat, cathode, okay? The last piece to allow this reaction to occur is this salt bridge, right? So if we are losing positive charge over here, we need to lose negative charges as well to keep that overall charge balanced. So our negative charges can actually come over and travel through this salt bridge and come over to this side where we are, right, we are increasing our positive charges, so we need negative charges to be in here, okay? So the salt bridge allows for this equilibrium, or allows for this reaction to occur, okay? It blocks that copper from actually going up the salt bridge, and it blocks that silver from going up the salt bridge. It only lets these small ions through, okay? So that's where our KNO3 salt bridge is going to be useful, okay? And then the last piece with this is that we have a voltmeter, okay? So we can measure this potential where we have electrons, like we said, traveling this way, right? Electrons traveling this way. Our electrons traveling, we can tell how many electrons are traveling through, okay? So that is our whole big electrochem cell, right? We're going to see this in the lab. We'll see this in the lab. And then here we get to start applying some math with it, okay? I'm going to pause and we'll come back.